So in electronics, there are many ways to increase the voltage of a voltage supply. So for example, if I have these two batteries, they supply about 2.7 volts in total, but I can actually use components on my circuit to boost this voltage up to 10, 20 volts even. To demonstrate this, I'm going to use a constant voltage source set at 5 volts. I'll turn this on so you can see it's outputting 5 volts. And it's connected to this strange circuit, which I'll explain in a bit. And the output across this resistor, I'm going to measure that. And what you can see is, so there's the output. And it's 9.6 volts with a 5 volt power supply. So how did this happen? This circuit is a astable PWM circuit using the 555 timer. So it's outputting PWM through this wire. And then I'm using a configuration to boost the voltage. You might have heard of a boost converter, which uses inductors and capacitors to boost. The way that I'm boosting is using a method called a charge pump. And I'll go over to my computer to demonstrate the circuit and how it works. This is the LT-SPICE simulation of the charge pump powered by a NE555 timer configured in a PWM mode. The charge pump, also known as the Cockcroft-Walton multiplier, uses a series of cascading capacitors and diodes to make this work. So I'll explain the circuit. First of all, this NE555 timer is configured in PWM, and I'm not going to explain more about how it's achieving the PWM. You can watch my previous videos where I go into that in detail. But essentially, the output on this node is a square wave output. So let me just show you in a simulation. So this node, let me decrease the time. Okay, there you go. And yes, so basically this output here, facing the capacitor, has a on and off cycle. It's normally a square wave, but because it's loaded with this circuit, it skews it to this sort of sharp edge. And so what's going on is on the off cycle, so when it's low, the current will come in through this diode into this node and basically make the current of this node exactly the same as the current to the left side of this diode, because it can flow within the two. So when this node exceeds the current of this diode, it no longer flows. Therefore, it basically fills up the voltage of this node through this diode, which goes to VCC when the PWM output's low. And then all of a sudden, when the PWM output's high, now the capacitor C3 here tries to maintain its voltage. So capacitors don't change voltages immediately. They take time. And when the capacitor pulls high immediately what you see is the voltage on the other side of the plate will pull high as well with the same amount of increase. And so therefore, now all of a sudden, the voltage on this node is higher than the voltage on this node because the capacitor through the PWM has pulled high. And then because the voltage is high on this node, it will start flowing through the capacitor, through the diode D3 to the next node. But it will not flow through this diode because this diode is now reverse biased. On the next node, there's a capacitor to ground, and the use case of this capacitor is a low pass filter. So basically, high frequencies get filtered and get shorted to ground, but low frequencies can pass through. And you essentially just cascade this many times. So here I've cascaded it 3 times. And yeah, so the net effect is basically on the off cycle of the PWM, the node basically gets filled up with charges from VCC. So it fills the charges up to some voltage, to the voltage of the next node. And then on the on cycle of the PWM, the voltage on this side all of a sudden jumps even higher than this side, and it gets pumped to the other side via the diode D3, and it never flows back on the down cycle, on the off cycle. So yeah, that's basically how a current pump works. Sorry, a charge pump works. And you can see the output that I've designed here. So when I rerun this, let's give it 1 second, maybe 2 seconds. And I'm just going to measure the output on this final node. So as you can see, the supply voltage that I'm giving is 5 volts, and I'm getting 16 volts back up. So more than 3 times, or approximately 3 times. And that's because I created 3 multipliers here. On the circuit I showed live, I only had a single multiplier, which is why it was 9 volts. But here, I scaffolded this many times. And you can actually scaffold this lots more times than just 3. In fact, the more times you scaffold, the higher the voltage will be. And one of the uses for the charge pump is it was used in the Manhattan Project to increase the voltage up to millions of volts in order to power particle accelerators to split the atom. And here's a picture of that used to split the atom. So you can see every one of these rungs is a cascaded stage in the charge pump. So some things to understand are what impact does the duty cycle have on the output voltage? So this actually depends a lot on the values of the capacitors. Because what's happening is on the off cycle, the charges need to flood in from VCC at every stage. So in this case, it's flooding in from here. In this case, it's flooding in from here. And your off cycle needs to be long enough such that the charges can take their time to increase to the same voltage as the next stage. And basically, it needs to also fill up this capacitor. And then the on cycle, the charges need to flow from this stage onto the next stage. So it needs to have an on cycle long enough to sustain that flow. For example, if your on cycle was too short, not all of the voltage from this node can be pushed to that node before, not all of the charges before the on cycle ends. So the maximum voltage output will depend on the values of the capacitors and the timing related to how fast charges flow through these diodes. And I'm not going to, go over the math in detail, but for this circuit, because the capacitors are identical and the resistances are basically zero, or identical as well across these diodes, it turns out that a 50% duty cycle is the best, because if I increase the duty cycle, the charges won't have enough time to flood in from the D2 diode, and if I decrease the duty cycle, the charges don't have enough time to flow through D3. So for example, suppose I change this to 100, and this is how you vary the duty cycle of a 555 timer, and then I run it again. You can see that it peaks out at just 14 volts here, rather than 16. And likewise, if I switched from here to 4900 and this one to 100, likewise you see 14 volts being calculated, and it charges up much slower as well. So the voltage ultimately takes a bit of time to reach its peak voltage compared to when the duty cycle is exactly 50%. So when it's exactly 50%, you can see that not only is the peak voltage higher at 16, it charges up to that voltage much faster at the output. So one question I had when I was two questions actually that I had when I was looking at this is, first of all, is there any limit to this cascade? So we know that in the Manhattan Project, they cascaded the 1, 2, 3, 4, 5, 6, 7, 8, 9 times and got it up to millions of volts. But can I cascade this forever, theoretically, on a perfect circuit? And the answer is, it depends on what you mean as a perfect circuit. If the source, input source voltage has input impedance, there's a concept called impedance matching, which will limit the maximum amount of power that the source voltage can output. And this maximum power is consumed through this final resistor output. So basically in impedance matching, the maximum power is conserved, and if you increase the final voltage, you can only get a certain current out of it. So that's the limiting factor here. If you have too many cascading stages, the final output cannot have a very high current, because the source voltage has a input impedance which limits the possible power output. And I won't go into this in detail because I'm going to explore input impedance and a concept called impedance matching in a future video. The other thing I wanted to go over was, well, where is the energy actually coming from? Because we have a 5-volt input into the circuit, and we have a over here a 16-volt output. And because of Kirchhoff's current law, the current in and current out must be conserved. So if we just look at this this bit of the circuit, the amplifier stage in isolation, what is the current in? This capacitor does not have any current going in, so the current is only coming through this VCC supply, and these capacitors don't have any net current flowing out, so the net current flowing out is through only this load, right? And we know that the voltage of the current coming in is 5 volts, out to 16 volts, and we know that the current coming in needs to equal the current coming out. So then, obviously, energy is gained in the circuit because P equals IV. I stays the same in and out, but V increases.
So power is somehow gained in the circuit. And I first started thinking, is it these sort of capacitors, the ground that's sort of, you know, sucking up energy and things like that? But it's actually not. The reason why power is gained in this amplifier is entirely because of the pump. So this is actually where the energy comes in from. Is this PWM itself? So let's not talk about how the internals of the PWM works, but if we assume that it has enough power to produce these square waves, every time it bumps the voltage, it needs to push a ton of low voltage current through here. And that's actually where the work comes in. It's coming in through the output pin of this PWM circuit. And ultimately, what's actually happening inside of the current regulator and the NE555 is it's trading low voltage current. So it's trading a voltage drop on lots of current in order to achieve a high voltage gain on a small amount of current. So there's a lot of current that's losing voltage inside of this pump in order for this circuit to be gaining voltage on a smaller amount of current. If you think of the current and voltage analogy of electricity as water flowing through pipes, what's happening inside of this 555 timer is there's a sort of current buffer that's essentially dropping, let's say, 10 kilograms of water 1 meter in order to lift 1 kilogram of water 3 meters in this output circuit, in this charge pump circuit. So essentially, the 555 is acting as a pump for this sort of ladder. Yeah, and that's it for the video.